All right, let's get into it. Today, we're digging deep into chemical reactions. And you see a nice clean equation and you think, okay, I get it. But here's the thing. There's almost always a hidden story, a secret set of steps happening behind the scenes. So let's play detective and see what we can uncover.
So, let's set the scene for our little mystery. We're going to start with what looks like a totally straightforward chemical reaction. This is our case file for today.
And here it is. We've got nitrogen dioxide and carbon monoxide on one side, and they turn into nitrogen monoxide and carbon dioxide on the other. Everything's balanced, everything looks tidy. It tells us what we start with, our reactants, and what we end up with, our products. Seems simple enough, right?
But what if that's just the book cover? Like you're reading the first page and the last page of a novel and just completely skipping the actual plot. What really goes on in between the start and the finish? That's where the real story is, and that's what we're going to unpack.
So if that neat little equation is just a summary, what's the full story? Well, it's a hidden journey. A chemical reaction doesn't just, poof, teleport from reactants to products. No, it has to follow a very specific route, a whole series of individual steps.
Think about it like this. Say you're going to a concert. You don't just magically appear in front of the stage. You have a whole process, right? You probably walk to a bus stop, then you take the bus across town, and then maybe you hop on a subway for the last little bit. Each part of that trip is a crucial step to get you to your destination.
And that whole step-by-step route in chemistry, it has a name. We call it a reaction mechanism. It's the how behind the what. It's the detailed travel itinerary that the molecules are following, not just the departure and arrival airport.
And each single part of that trip, that's what we call an elementary step. So the walk to the bus stop, that's one elementary step. The bus ride, that's another. Each one is a totally separate event, a single collision that gets the whole reaction one step closer to the finish line.
So what's the actual two-step journey for our reaction? Well, chemists have done the experiments, and they think it looks like this. And whoa, right away, this is weird. Look at step 1. It's not an NO2 molecule hitting a CO molecule like the main equation suggests. It's two NO2 molecules crashing into each other.
And you probably just spotted the real mystery guest in this story. This NO3 molecule, nitrogen trioxide. It gets created in that first step, but then it's immediately used up in the second step. I mean, it wasn't there at the start, and it's not there at the end, so what in the world is it? This guy has a special name. It's a reaction intermediate. It's just a temporary player in the game. Think of it like a bus transfer ticket on your trip to the concert. You get it after your first ride, you use it to get on the next one, and by the time you arrive, it's gone. It was absolutely essential for the journey, but it's not part of the beginning or the end.
Okay, so we've got our secret journey, we've got our mysterious intermediate, but that brings up another huge question. What actually controls the speed of the whole thing? Why are some reactions basically explosions and others take days? To figure that out, we have to find the bottleneck.
Let's go back to our concert trip. Let's say your walk is 5 minutes. The subway ride is a quick 10 minutes. But the bus gets stuck in gridlock traffic for an entire hour. What part of that journey determines when you arrive? The bus, of course. The slowest part of any process is always what controls the overall speed.
And that slow, traffic-jammed bus ride has a perfect name in chemistry. It's called the rate-determining step. This is the one step that creates a traffic jam for the whole reaction. It doesn't matter how fast all the other steps are. The entire process can only move as fast as its slowest, most sluggish step.
So for our reaction, which step is the bottleneck? Well, the evidence from the lab shows us that step 1 is the slow one. That's our traffic jam. The second step is super fast, but it doesn't matter. It's like a world-class sprinter who has to wait for a toddler to finish their part of a relay race. The whole thing is dictated by that slow first step.
Now here's something that's really important to remember. A reaction mechanism is a theory. It's our best guess. We can't actually shrink down and watch these single molecules collide. So, just like a good detective, A chemist has to be sure their theory fits all the evidence. And for that, we have a little checklist.
So for our two-step theory to be considered plausible, it has to pass two really critical tests. First, you have to be able to add up all the individual steps and get back to the overall reaction we started with. And second, and this is the big one, the mechanism has to predict a reaction speed, a rate law, that perfectly matches what scientists actually measure in a lab.
Let's run our theory through the checklist. First up, do the steps add up? Okay, let's see. We've got our mystery guest, NO3, on the right in the first step and on the left in the second step. So we can cancel it out. It's gone. We also have an NO2 on both sides, so one of those cancels out too. So what are we left with? NO2 plus CO gives us NO plus CO2. It's our original equation. Requirement 1. Check. Okay, now for the moment of truth. On the left here, this is the hard evidence from the lab. Scientists have measured this reaction and they've found that its speed, its rate, depends on the concentration of NO2 squared. That's a fact. So what does our theory predict? Well, we said step 1 is the slow step, so it determines the rate. And what does step 1 depend on? It depends on two NO2 molecules colliding. So our theory predicts the rate should be, drumroll please, dependent on NO2 squared. Look at that. It is a perfect match. Our theory holds water.
So after all that detective work, what's the big idea? What's the major takeaway here? It's that the thing you see on the surface, that simple equation, is often just a very neat summary of a much more messy and way more fascinating process.
And this really is the key. A balanced equation tells you what you start with and what you end with. But the mechanism, that hidden journey, that tells you how it all actually happens. It shows you the real collisions, it reveals the temporary players, and it points out the bottlenecks that define the whole process. And for chemists, trust me, figuring out the how is everything.
And you know, this idea that the how is often way more important than the what, that goes so far beyond chemistry. It kind of makes you wonder, doesn't it? What other simple summaries do we just accept in our everyday lives that are really just the cover for a much deeper, more complicated, and honestly, a much more interesting story? Something to think about.